Hello, this video is entitled Intro to Hypothesis Testing. Now, hypothesis testing is a branch of inferential statistics where a claim about a population parameter, such as the mean, which is all we're going to be referring to here, but you can perform hypothesis tests on proportions, standard deviations, differences of means, but we're just focusing only on the population mean. So in other words, we're going to make some claim, somebody claim about a value, and then we're going to use statistics to test to see whether we agree or disagree with that claim. Now, every hypothesis problem is set up with a pair of statements. They come as a null hypothesis, and then we have the alternative hypothesis. They come in pairs. This H sub 0, I like to call it ho, just for fun. The ho will always have a statement of equality, meaning it's going to be less than or equal, or greater than or equal. And the alternative hypothesis, sometimes you'll see it as H with an A subscript or H1. Either one of those mean the same thing. Just depends on what book is being used. That's a statement of inequality that is the complement or also opposite of whatever the ho is. So less than or equal to, and greater than, equal, not equal, less, greater than or equal to, and less than. And here they are. Here are the three possible setups for hypothesis tests symbolically. They have to look like this. Anything that does not look like one of these three is wrong. Like, for example, this last one. You have a null with the ho of equal pairs up with not equal. You can't reverse those. You can't have the ho not equal and the ha be equal. That's not correct. These can't be reversed. They have to be in this order. And mu is just going to be sitting there in the statement as variable mu. Mu 0 will be whatever the given number we're testing against the claim. So in other words, this one might say mu greater than or equal to 20, and therefore this would say mu less than 20. So the mu 0 will be a numerical value. The mu here will just stay as variable mu. Now, because these statements all come in pairs, when you see a hypothesis problem, you'll have enough information for sure to get either the null or the hypothesis statement. That's what we call the claim of the statement. That's whatever that somebody's claiming, that's their hypothesis. Now, all we have to have of one or two, one because we can get the other. So, for example, if we know they're claiming that the mean is greater than 10, for example, we know that greater than, by definition, has to be a ha, and then it would pair up automatically with the ho of less than or equal to 10. So they have to pair up like that. So long as you know one, you can get both. Suppose we had, they told you we think the population mean is equal to 6. Well, if it says equal, that means that is the ho, and then the ha would be not equal to 6. Now, this little chart here just kind of shows some common phrasings. I don't like to get too tricky with this, but it just kind of can read through those and see what they, produce symbolically. Like is or of is going to be equal, is not, differs, not equals. So at least means greater than or equal to. So it's important to realize phrases that, like at least and more than, you need to realize those aren't exactly the same thing. Their arrows point the same way to the right, but at least would have an equal below it because it means greater than or equal to. So fewer than, less than, and then no more than, or at most, means less than or equal to. So we're starting out here. Let's see if we can take a statement and come up with we'll identify what the claim is, and we'll identify what the statements are, the ho and the ha. Okay. A consumer analyst reports that the mean life of a certain type of automobile battery is 74 months. All right, so I would look at this, and I would think, all right, is. Is means equal. By definition, those three things above, those three pairs we showed before, is means equal. Equal has to be a hoe. So H0 mu equals 74, that's the claim. And then by definition, it automatically pairs up with mu not equal to 74. That mu has to be there. There's no, it's not, you can't say like ho equals 74 or ho or ha not equal to 74. You know, if that was ever an answer choice on an exam, you would not pick that. The mu has to be there for sure. So that was the claim because it gave is there in the wording, and then equal automatically then pairs up with not equal. So you see, as long as you have one of the two, that's all you need. Oh, let's see. Let's back down here. The next one. A company claims that its brands of paint have a mean drying time of less than 45 minutes. Okay, less than, using those three definitions on the first page, less than is always a ha because it doesn't contain equal, and it pairs up with a ho of greater than or equal to because that way they're opposites. Remember, the ho always has the equal. So we have the ho will be greater than or equal to 45, and the ha will be less than 45, but this time the claim is the ha. So the claim can be either the ho or ha. It just depends on what symbol is the claim producing. If it's producing a symbol that represents ho, it'll be the ho. If it's a symbol that represents ha, it'll be the alternative, ha. That's how we determine it. You claimed the mean score for all NBA games for a particular season was more than 100 points per game. All right, more than is greater than. Greater than is a ha. So that would be your claim, and then by definition, it would automatically pair up with a ho of mu less than or equal to 100. I'll just scroll back up there real quick. It's all going back to these three right there. Those are the three possible pairs. Now, let's talk about something called types of errors and level of significance. This video is primarily terminology oriented and just setting up some things we need to know. Subsequent videos will actually be more calculation based. But there's a lot of terminology and a lot of things to understand that is the purpose of making a separate video I thought was worth doing just on this. Kind of familiarize ourselves. So we reach one of the two conclusions. And we're basically testing the null, the ho. So we reject the null hypothesis, or we fail to reject the null hypothesis. That means we either reject the ho, or we fail to reject the ho. Now you got to be careful with this number 2 here. Failing to reject the ho does not mean we accept or love the ho. It doesn't mean we wholeheartedly agree with the ho. It just means that we feel we don't have the statistical evidence to dispute the ho. That, it's kind of close, but it's not the same thing. That's why the answers aren't either reject or accept. It just means you fail to reject, going, okay, we might not think the ho is accurate, but we have no statistical reason to dispute it. Okay, we'll talk more about that. Now, there's two types of errors you can make in this, statistical errors you can make in this process. Now, this does not mean these are computational errors. I'm not talking about errors as in mistakes you made. It's just anytime you're using samples to predict a value from the population, you can't be 100% certain. Unless you say something ridiculous that, the value is between negative infinity or infinity. Well, yeah, okay. But that's not exactly useful. Kind of relating, going back to confidence intervals. If you calculate a 95% confidence interval, that means there's a 95% chance that the population means fits in that interval, but then there's a 5% chance it does not. And you won't know if your interval did not include the mean or not. You wouldn't know, but there's a 5% chance that it did not. That's what we mean by it's kind of a process error, not a calculation error on your part. So a type 1 error means we reject the null hypothesis when it was true, if it turned out to be true, which we don't really know, obviously. But yeah, that would obviously be a mistake, wouldn't it? If you rejected the hoe and the hoe was true, yeah, that would obviously be wrong. And then a type 2 error occurs if we fail to reject the null hypothesis if it is false, meaning the hoe was wrong and we did not say it was wrong. So that seems like that would obviously be a mistake, and it's a different mistake, so therefore it has a different name with it. So there's two types of mistakes that can be made in the process. Here they are redefined again. We're not too worried about this beta for the type 2 error. We're only interested in the type 1 error. But it's basically sort of saying what I'm saying. So if they're throwing in phrases here, type 1 error, false alarm, and type 2 error means a missed opportunity. You didn't reject it when it was false. You don't have to worry about those phrases really, but anyway. So let's take a look at these. So, it's kind of 4 scenarios that can happen in a hypothesis test, and 2 of them are meaning they would have been correct, and then the other 2 are the errors. Now, don't misinterpret this chart, and this doesn't mean these are all equally likely to happen. That's not true, fortunately, because if you had a 50% chance of making an error here, this would not be a very good process. So it's not equally weighted, but it's just saying, for example, kind of read the row with the column. So if you did not reject the hoe and the hoe was true, that would be correct. In other words, you didn't say it was wrong and it was correct. So that's good. Right below it, you rejected the hoe when the hoe was true. You made a type 1 error. Let's go over here to the second column. You did not reject the hoe when the hoe was false. You made a type 2 error. And the bottom right one is, you rejected the hoe when the hoe was false. Well, that would be a good idea to reject the hoe if the hoe was false, and that would be a correct result. Okay. Now we have a value called the level of significance. That's a value that's given to you in a problem to reach a conclusion. And it's just sort of like telling you, if like a confidence interval, you have to be told, well, find the confidence interval. Well, what's the confidence level? Same thing here. This is a number also called a level that you have to be given. It's the maximum allowable probability of making a type 1 error. Now I say it has to be given. Of course, if you were performing statistics yourself, you could choose what you wanted it to be, just like you could choose whatever confidence interval. I'm just talking about from an academic standpoint. It's a value that's given to you in the problem. It's denoted by the Greek letter alpha right here. It's okay if you don't know alpha, but just you can kind of recognize it. That would be good. Some common values of alpha are 0.01, 0.05, 0.10. That doesn't mean we always use those. It's kind of like when we said for confidence intervals, the most 3 common are 90, 95, and 99, but you're not restricted to those. Now here's a non-numerical example that I'd like to sort of explain the type 1 and type 2 errors to give you kind of a feel for what they mean here. We're going to look at the criminal justice system and somebody on trial for whatever reason. And let's say the null hypothesis is always the defendant is innocent. It's supposed to be presumed innocence. That's the idea. And it's up to the prosecution to try to prove to reject their innocence. And then the alternative would be the defendant is guilty. So let's kind of focus on the types of errors here. What type 1? Let's see what a type 1 error is. Now, if we go back up to that definition, a type 1 error, I'm not going to scroll back up, but you can go look at it. It's rejecting the hoe, the null, when the null was true. In other words, you rejected their innocence, and they were found guilty when they really were innocent. That's bad. The idea is the justice system's supposed to be, set up to where you minimize that now. as much as possible. You don't want to send an innocent person to jail. A type 2 error is you fail to reject the hoe when the hoe was false, meaning the defendant really wasn't, they really were guilty, in other words. Turned out they're not being guilty, but you did not reject their innocence, meaning a guilty person was found not guilty. So they basically got away with it. So hopefully that doesn't happen too often, but that's not as bad as an innocent person being convicted. Yeah, you don't want if the occasional guilty person gets away with it. But anyway, I'm not a criminal justice professor, so I should probably stay in my lane and stay focused here. But one thing I'll mention this before I move on, and if you're talking about the idea of what I was saying about you either reject the hoe or fail to reject the hoe, whenever you hear the verdict read on any legal type of TV show, they don't use the word innocent here. Use the innocent here is okay, but when the innocent, they don't use that. They don't use that wording. They say the defendant is either guilty or not guilty. Now, if you're deemed not guilty, of course, it means you're free to go. But what that's saying is, not guilty really means, okay, we might not totally believe in your innocence 100%, but we don't have the evidence to reject your innocence. So they use not guilty. So not guilty, but that means you're free to go. But, you might not have been innocent, but we don't think the evidence proves you're guilty, in other words. So that's kind of like, just think about that. Then not guilty. But yeah, if it doesn't prove you're innocent, let's see. But, the defendant's free to go, obviously. Yeah, these conceptual problems can actually be a little tricky, how you think through these. Probably more difficult than when we start doing the calculations and subsequent videos here. You have to think real carefully here. All right, we got a hoe and a ha here. The hoe is that mu is less than or equal to 47. And I mentioned at the very beginning that you might see either HA or H1, same thing. Mu greater than 47. So this answer D is kind of nonsense here. It won't be none of the above. It's either going to be correct decision, type 1 error, or type 2 error. That's the way it would be on an exam, too. It's going to be one of those three. That's just kind of I wouldn't even put that answer there. I wouldn't want somebody to pick it by mistake. Now, what result if we conclude that the mean is greater than 47? So, if we said it's greater than 47, that means we favored the alternative, which means we rejected the null. We rejected the null in favor of greater than 47. Now, it says when its true value is really 52. Okay, if it turned out later that we found out it was 52, and we're saying it's more than 47, that is a correct decision. Because it turned out being more than 47. Now I'm going to take the same problem and make a slight change on it here just to make you think about this. Now suppose everything's the same and I change this to 42. And it's going to be one of those three answers still. You can probably tell it's not going to be the answer we just had, but it's going to be one of the errors here. And let's think about this. So the same thing, you rejected the null in favor of greater than 47. What if it turned out that the mean was really 42? Well, 42 is not greater than 47. That means the hoe would have been true because 42 is less than 47. So we rejected a true hoe in favor of the alternative. So by rejecting the hoe and the hoe is true, it would have been B. We would have committed a type 1 error. Because that's rejecting the hoe and the hoe is true. Yeah, you really got to think carefully. Well, this is obviously the first example you've ever seen on it, so that's certainly going to make it more difficult to understand. So hopefully you hear me explain all three of these. That will help you be able to think through this a little bit better. Okay, let's take a look at this next example. Mean running time for a certain flashlight battery has been no more than 9.1 hours. So they gave us the ho and ha here, but we could have done this without it, because we could have that no more than is enough of a phrase to tell us that means less than or equal to. Since it has an equal, it has to be the ho, pairs up with a ha of greater than. And then they want to perform a hypothesis test to determine whether the mean running time has increased as a result. So let's say that our sampling and calculations we haven't seen yet or whatever, but lead to rejecting the null hypothesis. In other words, we're saying it's wrong. So we're deciding whether it's type 1, type 2 error, or correct decision. Now here comes the part we need right here at the end. They didn't give us a number like the last example. They said if in fact the mean running time has not increased. So that means the ho is true. It did not go above 9.1, but we rejected the null hypothesis. So what happened is we rejected the null hypothesis when in fact the null hypothesis was true. By definition, that is a type 1 error. So had this said that this last part had said if in fact the running time has increased, if the word not wasn't there, it would have been a correct decision. Because if it increased, you would have wanted to reject the ho in favor of the ha, which was greater than. So it's the has not increased meant the null was true, and we made a type 1 error by rejecting the null when the null was true. And here's one more of these. Okay, they're looking to determine whether the SAT score has changed. They gave us the ho and ha here. I don't know if I would use change, but I would say is differs from or not. It's essentially equal or not equal, meaning when you say changed, you can't imply direction. No, in other words, less than or greater than. It just means, is it different than what it was before? So long story short, we're testing equal, not equal. Suppose the results lead to non-rejection of the null hypothesis. We did not reject it. Failed to reject. Okay, classifies what type of error or correct decision. If in fact the average math SAT scores of the students has changed from 500. So that means the alternative was true. So if we fail to reject the null hypothesis when it is wrong, obviously you want to fail to reject it if it was true, but if you fail to reject the null hypothesis when it's false, you have made a type 2 error. That is the definition of a type 2 error. All right, so it's, of course, I had the advantage of knowing those definitions. I didn't expect you to have those memorized when you were looking at those, but okay. Some more good terminology here: statistical test and p-values. Now, test statistic, that's going to be something we see how to compute using sample data later on. Combine that with the level of significance, we can reach our conclusion to the hypothesis test using our data. In other words, do we reject the ho or do we fail to reject the ho? Now we're going to talk about something called the p-value. If assuming the null hypothesis is true, or just, that's fine, if the null hypothesis is true, a p-value of a hypothesis test is the probability measure of how likely the sample results are true. Meaning, is it accurate that the sample results are identifying that the null hypothesis is true? The smaller the p-value implies that the less likely that the sample results are less likely to be true, and that's what we're going to learn in a subsequent section of meaning that's going to lead to rejection. Maybe I shouldn't have spoiled the surprise, but that's okay. All right, so let's look at the p-value sort of visually. We're going to be one section. We're going to be doing the z distribution, so it's going to be areas under the normal curve. The t distribution will be a little bit different. But here's our good old normal curve. Now those three defined test pairs that we had on the first page, they now have names. You know, not exactly pretty names, but functional names. This test where the ho is greater than or equal to and the ha is less than, that is defined as a left-tailed test. A left-tailed test is your test statistic is going to likely end up on the negative side of the z. And I say likely, it could end up on the positive side, but that's pretty rare. That actually means someone set up a really, really bad test statistic, bad hypothesis, excuse me. Not the test statistic. You don't set that up, you calculate it. But someone made a kind of an outrageous hypothesis claim. But anyway, it should fall, you know, on this side, the negative side for the z. And the p-value is actually the area under the normal curve to the left of that test statistic. Now the next one, when the ho is less than or equal to and the ha is greater than, that is defined now as a right-tailed test. The test statistic should likely be on the positive side for a right-tailed test, and then the p-value will be the area greater than the test statistic to the right. The next one's a little tricky, but once you get used to it, you'll be all right. The last one, equal, not equal, is a two-tailed test. Essentially, two tails implying that if something is not equal to something, it can be not equal to it by being less than or greater than, you know, both sides. But now this one, the test statistic might come out negative or positive. That doesn't matter. And it's on both sides, essentially, wherever it falls. What you're looking at here is, you know, you can write both of them down if you wanted to draw a picture. You don't have to. I'll kind of explain it. Right here I explained how to calculate it quickly if you're using the Z chart. Next section we'll be looking more at the calculator. But whether it's positive or negative, you're not expecting it. Like I said, the other two, left-tailed, you're expecting the Z to be negative. Right-tailed, you're expecting the Z to be positive. Here, it doesn't really matter. But what happens is there's an area to the right of that positive Z, and there's an area to the left of the negative Z. Those are each half of the p-value. Half, not the full p-value. So if you add those two red pieces together, that's going to be the p-value, the total of the shading. Now, I'll scroll back up to these to show you how to get them using a chart. The normal chart is kind of reviewing how we find area under the normal curve like we've learned in the past. So if it's a left-tailed test, since your Z distribution automatically gives you the area left, you'll just look up the test statistic. It's the same kind of stuff here. On a right-tailed test, your test statistic is positive, so you're going to flip it over and look up the negative. Just change it to negative, look it up, that area, that'll be your p-value. Now what you want to do here is you still want to use this negative idea. So what happens is whether it's negative or positive, you would look it up as if it was negative. So if it's negative 1.25 or positive 1.25, either one of those, you would look up negative 1.25. Yeah, it's kind of a little bit different. You just get you get the negative. It's either negative, leave it negative. If it's positive, make it negative. I'm just trying to find different ways to say that. You find that area, but since that area is going to be half of your p-value, you've got to double that result. I think I already have the normal chart up here. If not, I can bring it back up. But Yeah, there we go. So it's telling we got a two-tailed test. It's giving you the z. Find the p-value. Now I drew this picture because I put the 2.34 in red, meaning that was the given p-value. But for two-tailed, it automatically, whether it's negative or positive, represents both sides. So I just do 2.34. I shaded the right part, and then wrote in negative 2.34 and shaded the left part. It includes both, but using the chart, all we do is look up negative 2.34. Let's go back up to the negative side here. Right here. 0096. But because it's a two-tailed test, and only because it was a two-tailed test, left-tailed, right-tailed, you don't have this 2 factor out in front. We double the result we get off the chart. So the p-value would not be the 0096, which it would have been if it would have been left-tailed or right-tailed. You have to multiply it by 2, and you'll get 0192. Now here's just a couple of questions setting up. Now, it's setting up the ho and ha like we did before. We've already done that. But now we're adding in the idea of giving it its proper name of the test that we didn't know before. So, all right, let's see. Alma claims the mean GPA for all UHD students is more than 2.9. All right, let's determine whether it's left-tailed, right-tailed, or two-tailed. So what I'm going to do is write down the ho and ha. All right, more than means greater than. So your claim is greater than, which will be a ha, because all greater thans are ha's. And it pairs up automatically with a partner of less than or equal to 2.9, because that's one of the 3 pairs. Now, you scroll back up and look at that. I don't expect you to know these just yet. But anyway, this particular pair we saw a little while ago is called a right-tailed. So that's the new part of this process now. We call that right-tailed when it sets up like this. Lucy claims the mean GPA for all UHD students is 2.8. Is means equal. Equal is always a ho. So this time, the claim just follows the symbol. In other words, more than, claim went with the more than is a ha. Equal, claim was equal happens to be the ho. So sometimes people get confused, the claim can be either the ho or the ha, just depending on the wording of the claim. And by definition, equal, not equal, is called a two-tailed test. Here's kind of a little summary page here. Here's something I was saying earlier, that failure to reject the null hypothesis is not proof that it's true. It says you can never prove the null hypothesis is true. You can just not reject it. Yeah, this is very good wording here. If you fail to reject the null hypothesis, you can only conclude that there's insufficient evidence to warrant its rejection. Okay, here's some, I don't think you have to know these, verbatim, but null hypothesis represents the current belief in a situation. Okay. The H1 or HA, depending on what book you're using, is the opposite and represents research claim or inference you would like to prove. Because if you were setting up a hypothesis test of what you think was going to be the result, if you were doing this yourself, since, failing to reject, we've said, is not a strong statement to identify the ho, but rejecting the ho is. Rejecting the ho in favor of the claim, the ha, makes the ha strong, believable. So you can't really support the claim all that well. So what a statistician would do is if they're expecting, now they might not, you can't just reject it if the data doesn't warrant it, but if they think some result's going to be more than, they would make sure they set it up. They wouldn't use greater than or equal to and make that the ho. They would use greater than as the ha, and then hopefully the data and the results would lead to rejection of the ho, which would have been less than or equal to, in favor of the alternative of greater than. Then they would feel strongly about that greater than result. Yeah, you can feel good about the ha if you've rejected that ho. That's just that's not absolute proof. Once again, it's just statistical proof. Yeah. So this one tells you if you do not reject, you have failed to produce. Well, yeah, you have failed to prove the alternative. You also haven't proven the null either. Yeah, the H0 and the HI, the HA, H1, whatever, you always use the population. We're going to be using sample means in our calculations, but the statements, because you're actually testing the population mean, so that makes sense why that's that way. I don't really agree with this part. I think I should have taken this part out. Well, I guess it contains an equal sign. Don't interpret that as being, everyone. Some books use equal for all the hoes. I don't, but it has some form of equal. In other words, stick with what we've already just talked about. It's either equal, less than or equal to, or greater than or equal to. Don't imply this means always equal here. So I think that's not what they're implying, but some books do. Well, all right. That concludes this video on the intro to hypothesis testing, and we'll have future videos where we actually perform hypothesis test using data and calculations, and I'm sure that's going to be lots of fun.